So in this third video that introduces you to chi-square distribution, we're going to do our first and second goodness of fit tests. Now, I will show you the way to use the GOF test on the calculator, and I'll also show you how to do it by hand in case you have a calculator that's older than the TI-84 Plus. Now, in this video, we are going to do two problems which are preference, no preference problems. Now, I will show you through this video how you would identify whether the problem is a preference, no preference problem, or if it's testing to see if the data matches the distribution. So let's go and start with this problem. Employers want to know which days of the week employees are absent in a 5-day work week. This is important because you can maybe, plan schedules around it and offer incentives to maybe come in, during some of the days where more likely people are going to claim time off. Now it says in the second sentence, this is the key here because this is going to establish the preference, no preference problem. It says in the second sentence, most employers would like to believe that the employees were absent equally during the week. This implies that there was no preference, is that absences were equally distributed Monday, Tuesday, Wednesday, Thursday, Friday. And there's an old saying that you never want to buy a car built on a Friday. That is to basically state that there's probably more absences closer to or right after the weekend. And we can take a look at this table here because it says, suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. And so the results were distributed in this table. Now, it's important to see that there might be a preference because you can see Monday and Friday had higher totals than the other days, but the other days weren't too far away from them. So was Monday and Friday big enough statistically to say that, that there is a preference when most people take days off? So let's get this problem started. So we have here a total. The total is nice to have. I kind of like to do my addition from left to right. And even though the problem does state the number of managers who was surveyed, it does help to just double check that 15 and 15 make 30, and 12 and 18 make another 30. So the total we have is 60. Now these are the observed. This is what the managers observed, but this is not necessarily what they expected. So step 0 is to finish this table of observed and expected. Now you might begin to wonder, what are we actually expecting? Well, what we're expecting is we're expecting that the absence to be distributed equally during the week. So if 60 managers were asked and each manager was expected to give an equal distribution, then what we would do is we'd have that total of 60 divided by the number of categories, which in this case is 5, and 60 divided by 5 is 12. So we should have 12 for each of these days. Now what you're noticing is that they're not 12 for each of these days. And when we subtract the observed minus the expected, you'll see that we will get a difference in some of these. 15 minus 12 is 3. 12 minus 12 is 0. 9 minus 12 is negative 3. And same with the next one. And then what we have here is 15 minus 12, which is 3. Now, because this is a chi-squared problem, the negatives and positives actually will get kind of eliminated here because we're going to be squaring these numbers in step 2. But we should probably focus on doing things in order. So we did our observed and expected and found our differences here. We are also going to now do our null and alternative hypothesis. The null hypothesis is someone is going to be basically saying, no, there's nothing weird here. So there is no preference. There is no preference. That's the null's position. No preference on which day I'll put S in parentheses so you can say either day or days. Which days workers are absent. So the null hypothesis is going for what was expected, that we can't really plan for it. It's going to be equally distributed. The alternative hypothesis, which is H sub A or H sub 1, depending on the book you're using, is basically saying the same thing with a little difference. Instead of saying there is no preference, there is a preference on which days workers are absent. I'm using little quotation marks to basically use the same sentences up above, except changing the word no to A. So the null hypothesis is saying, yep, they're equally distributed. Monday through Friday, we're going to have the same number of workers, usually gone. That's going to be our most popular day. And the alternative is like, no, I think there are preferences here. It's not establishing what the preference is. It's just saying there is one. So what we're going to do now is we're going to take that table from up above, so keep that handy because I unfortunately cannot look at both at the same time here because I'm further down on the paper. I'm going to show you how to do this on the calculator and then show you how to type this in. So the formula for this is the sum of the observed minus the expected squared divided by what was expected. So it's the sum, and I should say it's the sum of this entire fraction here, and that is going to look like each column or each day category is going to have its own subtraction. 15 minus 12 quantity squared divided by what was expected, 12, plus, and then we're going to go to the next one, 12 minus 12 quantity squared divided by 12. And then we're going to go to the next one, which is 9 minus 12 quantity squared divided by 12. And then we'll go to the next one, 9 minus 12, which is the same thing, quantity squared divided by 12. And then we'll go to the very last one, which is the same as the first one, 15 minus 12 quantity squared divided by 12. Okay, so I'm going to show you how to type this into the calculator. I strongly recommend, if you have your graphing calculator, that after you turn it on, hit clear, make sure you're at a clear screen, and I would strongly recommend, if it's a newer calculator, click the mode key and change to classic mode instead of math print mode. I think the classic mode's a little bit better for long strings of data, and you might see this on the first page of your mode key, and if you have an older calculator, it may not even have the option because it is classic. So click the second key and then click the mode key to get you back to a clear screen. And now what I'm going to do is I'm going to carefully type in this data. So start off with a parenthesis above the 8 key and type in 15 minus 12. Parenthesis above the 9 key, and I'll use the square key, which is above the log key, so squared divided by 12. So that is the first column. The second column is superfluous because 12 minus 12 is 0, and 0 squared is 0, and 0 divided by 12 is 0. So you can type it in if you'd like, but I'm going to skip it. 9 minus 12, quantity squared, divided by 12. Plus, the same thing again. Sure, I could use some algebra to stop me from typing all this, since there's 2 of these and 2 of the first ones, but I'll just continue the pattern because most of you will probably not be looking any more deeply than just typing these in and being very careful as you do so. Okay, so now I have all 4 of these typed in. Again, the reason why I didn't type this in is 12 minus 12 is 0, and 0 squared divided by 12 is 0. Now, what we're hoping that all of these numbers are really small, because this will then give me a very, very small chi-squared test value. And we're about to witness a unicorn because this answer is a whole number. This answer is 3. That doesn't happen very often. It's much more likely that you're going to get a decimal, and maybe rounding to 4 decimals would be appropriate here. But we don't actually need to round to any decimals because the chi-squared test value is 3. Now, this chi-squared test value is going to be used for the lower limit, because in our calculator, we're about to go to chi-squared CDF, the cumulative formula. And we are going to use our lower bound as 3. This is our test value goes here. Our upper bound goes to infinity, but the calculator doesn't know the infinity symbol, so we're just going to trick it by putting a 1 with 99 zeros. Now, the degrees of freedom is the number of categories. The number of categories divided or subtracting 1. And so the categories, in this case, is 5, because we have 5 days of the week. And we could have interviewed 6,600 or 6,000 managers. We don't care about the number of managers. We care about the days of the week. That's what we're talking about. So the degrees of freedom is 5 minus 1, which is 4. So what I'm going to do is I am going to now type this into my calculator. So I'm going to click the second key, click the virus key, and then I'm going to go up from the bottom and look for my chi-squared CDF, which happens to be option 8 on my calculator. It may be different on yours. You also could have scrolled down to get chi-squared CDF as well. Now you see my lower limit is 3, because that was my test value. My upper limit is infinity, which I'm going to put 10 to the 99th power, and 4 degrees of freedom. Then I'm going to hit paste, and this is going to paste the formula right there so I can see it. Older calculators, you'll have to do this without the help menu. And then you hit enter one more time, and this gives you your p-value, your percent value chance of this happening. And the 0.5578 is the percentage value. So let me write that down here. P-value equals 0.5578. Now, is there an easier way to do this? Yeah, there sure is. If you have the newer graphing calculators, you can just type in this into list 1 and list 2, and it will do all the work for you. I'm about to show you that. So the first thing we need to do is remind ourselves, how do we even get to that screen that we need? Well, hit the stat button, and then hit the enter button. So a nice way to kind of remember this, if you want to enter the stats, you hit stat and enter. So let's go to the calculator. Let's turn it on, because it probably fell asleep if you left it sitting alone for too long. Click the stat button, then click the enter button. Now, if you have junk in your list 1 and list 2, and here you can just move up to the top and hit clear, then enter, and it will all go away. So now let's type in our list 1. So 15, enter, 12, enter, 9, enter, 9, enter, and then lastly 15, enter. Okay, now we're going to move to the arrow key over to list 2, and we're just going to type in 5 12s, hitting enter after each 12. This way you have my observed in list 1 and expected in list 2. Now for your notes, let's actually write that down. Okay, so in a list 1 we had 15, then 12, then 9, then 9, then 12, and in list 2 we had all 12s. This is in case you don't do the homework right after you take notes. Now the calculator will spit out your test value, also known as chi-squared. It will also spit out your degrees of freedom, which you might need to know if you're doing some XYZ or online homework. It might ask for that. And then, of course, the p-value will also be given to you as well. So let's get back to the calculator, and let's go to stat. Let's click 2 clicks over for tests, and then scroll down until we see chi-squared goodness of fit test. Be sure you choose the goodness of fit test. This chi-squared test will be done in about 3 videos from now, maybe 4 videos from now, but we need the GOF for the goodness of fit test. So again, if your calculator doesn't have this, then you have your option 1, which will get you the answer, just might take a little longer. Okay, so my observed is in list 1, my expected is in list 2, my degrees of freedom, I'm going to type that in as 4, and then we're going to go to calculate. The draw function isn't as robust on the calculator as it could be on the, so I'm just going to use calculation right now. So here we go. We got our 4 degrees of freedom, and we have our chi-squared value of 3, which matches what we did by hand. And check it out, we have our p-value, which also matches what we did by hand. So no matter which option you choose, if the work doesn't need to be put down on the online homework, you at least will get it either way perfectly. All right, so option 1, option 2 will work out great. Again, there might be some parts of the online homework which will require you to use option 1, so please take that into account. So what we have now is we have our p-value, which is 0.55, and our alpha, which is stated in the problem as 0.05. And this is another reminder that if you are not given an alpha, you got to just default a p05 and or default an alpha of 5%. And it looks like our p-value is 55%, so this is definitely not a rare event. So since p, which is 55%, was greater than alpha, which is 5%, we do not have sufficient evidence to reject the null hypothesis. There we go. Check it out. We do not have sufficient evidence to reject the null hypothesis. Okay, so for our final example here, we're going to take a look at one of our favorite kind of thoughts is like, ooh, how about drink flavors, for sport drinks, right? So imagine that you just wanted to see if people had a preference towards a certain flavor of sport drink, So let's check out step 0. Step 0, well, first of all, let's chalk this up to be our observed, because according to a survey of 100 people, the following results are what they preferred for sports drink flavors. With an alpha of 5%, can we be certain that there is a preference for a certain sport drink flavor? So, again, we should probably have a total column here, just in case there was any discrepancies in the story problem, and if you add up all 5 of these numbers, you do get 100. Which means that if you're expecting no preference, then what you need to do is you need to take your 100 and divide it by the number of categories. In this case, the categories, again, are 5. Don't always assume your categories are going to be equal to 5. It's just nice this way because it usually turns out to be some good whole numbers. So that means each of these is going to be 20. Okay, so we have 20 5 times. So we're noticing that there are some big differences here at the cherry and here at the grape, but the differences aren't as pronounced around orange and lime. But does the strawberry difference mean that there could be a preference? Well, only one way to find out is by using a hypothesis test. Now we are going to do the subtraction here, and 32 minus 20 is 12, and this minus this is 8, negative 4, negative 6, negative 10. Now again, these positives and negatives will eventually get scrubbed because in step 2 we're going to square them and divide by the expected value. But now we've finished our step 0 by marking out our observed and our expected and doing the subtraction correctly. Now in step 1, our null hypothesis is going to be a preference-no preference problem. So this means that our null hypothesis is saying there is no preference in sport drink flavors. No preference in sport drink flavors, but the alternative hypothesis, H sub A, is there is a preference in sport drink flavors. So instead of just getting 20 of each kind, you may pay attention to the data that we're selecting. Now, this is not stating which one's the best and which one's the worst. The alternative is just saying, no, you just can't buy the same of each ones. So we're going to do the calculations. We're going to do it the old way, or the older calculator way in option 1, and then we'll do the goodness of fit test style in option 2. So in option 1, we're going to take our observed, which is 32, minus our expected, which is 20, and then we're going to divide that by 20. Now, if you did your subtraction correctly, you can decide to kind of shortcut this busy work here and decide to just write the numbers down like this. We can write 8 squared divided by 20 plus, now this is going to be negative 4 squared divided by 20. Now it's important when you have a negative numbered squared, you need to put parentheses around it. And then we're going to go to negative 6 squared divided by 20. And then we'll go with negative 10 squared divided by 20. And I want to highlight this for another moment because if you do not use the parentheses squared, you will get the wrong answer. So let's take this last one for example. Negative 10 times negative 10 is 100. But if I type in negative 10 squared without a parenthesis, the calculator will get the problem wrong because the calculator will think you wanted negative 10 times 10, or even more weirdly, negative 1 times 10 times 10, because the calculator does not think the negative is needing to be squared. So that's why when you do a problem like this, 12 squared divided by 20, and you see I just did the 32 minus 20, I didn't need the parenthesis because 12 was a positive number. And same with 8 squared divided by 20. But when I do the next number here, which is plus negative 4 squared, 4 squared divided by 20, plus negative 6, and make sure the square is on the outside of the parentheses, not inside like I just typed. Make sure it's outside, divided by 20. And then finally, in parentheses, negative 10 squared. Now, I did have some students, from time to time raise their hand and say, but Mr. Anderson, couldn't I just drop all the negatives and just type them in without the parentheses? And the answer is yes, because algebraically, a negative number squared is going to be the same as the positive number squared, so you can just drop all the negatives and, use the absolute value of that. But again, most students are going to lean on option 2, which is letting the calculator do the goodness of fit test. And ladies and gentlemen, I want to welcome you to another unicorn because this is exactly 18. And again, a lot of times this is a decimal, but looks like I picked some examples that have whole number test values. So this is my test value for chi-squared. So my lower value is 18, my upper value is 10 to the 99th power, and my degrees of freedom is, again, 5 minus 1, which is 4. And we're going to type this into the chi-squared cumulative distributive function formula. So to do that, we're going to go back to the calculator, second vars, and I'm going to scroll down. I can see PDF, but I want CDF here. I want the cumulative distributive function, which goes to the right tail here, since we're going to go from 18 to 10 to the 99th power, and 4 degrees of freedom from the last problem. I hit paste, and it gives me the p-value of less than 1%. That is 0.1%. Look at that, 1, 2, 3, 4. I like the numerology there. So what we have is the p-value is equal to 0.0012. Okay, that was fun by hand. I guess, whatever you think fun is, right? I'm a math guy, so I thought that was pretty cool. But now I'm going to go hit the stat button, hit the enter button, and I'm going to move up to the top and hit clear enter. Move up to the top here and hit clear enter. And I'm going to type in list 1 into list 1. So, the observed into list 1, 32, 28, 16, 14, and 10. Okay. Then we're going to move on to list 2 and type in 5 data points of 20. Hit enter after each one. Okay, there's my 5 data points of 20. Now I'm going to go stat. I'm going to move 2 clicks over to tests, and I'm going to move down to the chi-squared goodness of fit test. There it is. There's my option, chi-squared goodness of fit test. Hit enter. It looks like I got my list 1, list 2 exactly where I want it. Degrees of freedom is 4, and before I hit the enter button for the not so surprising answer, because we also did this, without using the calculator, I just want you, for your notes, to write down what you had in list 1. 32, 28, 16, 14, and 10. And in list 2, a whole bunch of 20s. The book or the online homework will not be giving you list 2. You're going to have to figure out what list 2 is from the context of the problem. So now I hit enter on calculate, and I get the exact same p-value as I did. The degrees of freedom is the same, and the test value is the same. So let's summarize that. Chi-squared test value was 18. Our degrees of freedom was 4. And our p-value was 0.0012. Or, wow, less than a percent. Well, knowing that it's less than a percent tells me that since the p-value was less than alpha, okay, because our alpha was 0.05, since p is less than alpha, we have sufficient evidence to reject the null hypothesis. And remember, the null hypothesis is someone said, oh, you know, there's no preference, just get what you want. And I'm like, no, there is a preference here. And I don't want to, like, you know, just on this set of data, but, you know, maybe get a little bit more cherry, a little bit more strawberry, and maybe a little less of the other flavors, and most people will be happy. So that is the end of a preference, no preference problem. And I want to remind you before I let this video come to an end, the main reason why you can understand it's a preference, no preference problem is because either it says preference, or it basically talks about equally distributed numbers, or there's a complete lack of percentages in this problem. Sure, alpha is a percent. Alpha is always a percent or a decimal. But this problem and problem 2 has no talk about percentages at length. And I know this is going to be on the next video, but you can see just by reading the start of this problem, you've got this, this, and this. This is going to be a true goodness of fit test problem where we are not going to have a preference, no preference, null and alternative hypothesis here. So stay tuned to that last video here. This has now been the third of 4 videos talking about chi-square distribution with an emphasis on the goodness of fit test. And stay tuned for the next one where we're going to do 2 more populations and testing to see if they fit the given distribution.